On August 19th, during Tesla AI Day, Andrej Karpathy, Director of Artificial Intelligence and Autopilot Vision, dove into a topic that is distinctly not sexy, but absolutely necessary for modern machine learning: collecting and especially labeling data for training. After covering how Tesla Vision converts 2D images into 3D vector space and discussing how the cars can plan ahead not just for them, but for all other agents in the scene, and you can watch my previous videos on that linked above for much more on this, Dr. Karpathy broached the topic of how Tesla deals with the mountains of data its 2 million car-strong fleet produces now. And while I thought I'd be bored by this section of the talk, I was quite frankly blown away by how brilliant Tesla's data labeling strategy is, and also how much time, person power, and money Tesla has and is putting into labeling the best, most targeted data available. Along with the incredible neural network architecture, this data labeling is what is enabling Tesla to achieve what seemed impossible just a short time ago: full autonomous driving using only cameras. For those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. So this is episode 6 in the Tesla AI Day series. I'm going to assume you've seen the other videos because I'm going to reference them throughout this video. So if you haven't watched them, you might want to watch the playlist before, during, or after this video. The link's in the description as well as up above. As a lot of you are not machine learning experts, I think it's really important before we start to kind of lay out what data labeling is and why it's needed. So for machine learning, data is often labeled images or sounds or sentences or whatnot. It's some sort of information that's stored in a computer that then these neural networks or, K-means squared or A-star or whatever the heck it is, whatever it needs to be, can work on this data, and it can basically learn like a human being does in a, general sense, to do a better and better job at a given task or something like that using this data. So that's why it's super, super important. In the case of Tesla, the raw data is 2D images plus IMU data, which is inertial measurement units, plus GPS data, plus some other things. But really, that's not what they're using anymore. They're actually using a 3D vector space plus time plot now, and that's kind of what the subject of this video is, right? So basically what you get out of this is you get something that kind of looks like a top-down video game, and it's in sequences, and the sequences are actually fairly long. Ashok Eluswamy talks about this later on, and we'll get to this, but he actually talks about how the clips are 40 to 60 seconds long, which is much, much longer than I had assumed they would be. But anyway, the output is sort of like a top-down video game where everything is labeled, and that labeling is what the neural networks use to train on. So what is this labeling that we're going to talk about, and why is it so important? Well, labeling just means in an image, so a really, really simple one would be like a dog or cat image recognition type of neural network, right? So you have pictures of dogs and pictures of cats, but what you need to do is you need to label those pictures. Usually that would be a human being would write down dog in some sort of metadata. So there'd be a picture of a dog and then a label of a dog under it, and then a picture of a cat and a label of a cat. And you do that 1,000,000 times, and you throw all of those pictures with the labels at the neural network. The neural network takes a guess. At first, it's a pretty random guess, and so it's wrong most of the time. And that is used to actually train the network up. So in a sense, what labeling does is it allows semantic information to be attached to something, right? So a picture is, in essence, just a bunch of colored pixels. But what a human being is doing in this case, right, with a dog or cat, or much more complex in these situations with full self-driving, is that they're adding a label, some metadata or some semantics, saying we human beings recognize this group of pixels with these colors as a dog. And yes, there are other kinds of training that neural networks can do, like unsupervised training, but it seems like supervised training is primarily what Tesla is working on. And frankly, I was a little bit surprised at that. I actually thought that they were kind of moving towards semi-supervised or unsupervised learning, but we're going to get to that. Essentially what's happening is they've trained a neural network to do the labeling so that they don't have human beings doing it, which means that they get the advantage of having supervised training, which is much, much more efficient than the other methods without having to have human beings label it all. But anyway, it's really cool how they're doing this, but supervised learning basically requires a teacher to tell the student or the network if it's wrong or right. So you need data that has that information attached to it, metadata or semantic metadata. And like I said, with this data, the neural network makes a prediction. The software then looks at the metadata to see if the prediction is right. If it is right, then no problem, keep doing what you're doing. The more interesting case is when it's wrong. If it's wrong, you back propagate the error through the chain of connections to reduce that error next time. And by the way, if you're interested in how neural networks work, I've got some links up here. But anyway, as you might figure, and as I'm sure you've heard about before, what this type of machine learning needs is lots of data, and lots of well-labeled data, and lots of heterogeneous data, and lots of passes through this data in order to train the system. So that's why we need this data to train these systems, but think how hard this is to do with a human being. If you have a human doing this and you have millions to billions of images, that human being is probably going to quit, for one thing. But for another, it could take them decades or lifetimes to actually work through all of this data. So it's kind of like you've got these ultra fast computers, and then you're going back to the 19th century, right, where you have people like actually writing out equations by hand and solving them by hand. Computers are much, much faster at this stuff, but the problem is humans are good at semantics, so how do we integrate those two things? So to start thinking about this, let's go to the beginning of this section of the talk, where Dr. Karpathy discusses manual labeling and a bit of the history at Tesla of how this method was utilized.
Yeah, so the story of datasets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, it's not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them.
First, the parameters that Dr. Karpathy is talking about here are all the kind of, quote, knobs that make up a neural network. In essence, neural networks are just a giant machine with millions and millions of knobs that can model anything if the knobs are set just right. So you can imagine the old TV shows where they twist all the knobs and everything. And if you turn each of those in just the right way and you stick some stuff in, out will come the right answer. But all of those have to be adjusted just right. And all of the data is how you manage to train all those knobs to be set in the right position.
Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved.
So as Andrej says here, you need clean, or well-labeled, and diverse, or different cases, including lots of examples of edge cases, and big, or lots of miles, data. Also note here that Andrej said that this goes along with model development. This is because you can only train bigger and more ambitious neural networks with bigger and more ambitious data sets. And now he gives us a little history lesson.
Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets. Now, unfortunately, we found very quickly that working with a third party to get data sets for something this critical was just not going to cut it. The latency of working with a third party was extremely high, and honestly, the quality was not amazing. And so in the spirit of full vertical integration at Tesla, we brought all of the labeling in-house. And so over time, we've grown more than 1,000-person data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the US and co-located with the engineers here in Bay Area as well. And so we work very closely with them. And we also build all of the infrastructure for them from scratch ourselves. So we have a team we are going to meet later today that develops and maintains all of this infrastructure for data labeling. And so here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this.
So as you heard, the old way of doing this was no good. There was too much latency. In other words, Tesla would ask for labels on a given set of data, and it took a really long time to get it back, and quality, which meant that the data set was not particularly well labeled. And recall that human beings are prone to mistakes when doing repetitive tasks, and especially boring repetitive tasks. So, it's not surprising that they had a lot of errors, but this was an untenable situation. So Tesla went and fixed it by vertically integrating. And now they have a 1,000-person strong data labeling team, based in the Palo Alto area no less, which does nothing but label. And as I said, this is vertical integration. And just for a moment, let's consider the financial commitment of this. 1,000 people working in Palo Alto. I looked up, low-level engineer salaries, and it says it's about $80,000 in the Bay Area. So at a rough guess, this is around $80 million a year in salaries for people who do nothing but label data. So that's really putting your money where your FSD is, right? Anyway, back in the old days, which was like 4 years ago, this used to all be done in a 2D manner, one image at a time using bounding boxes.
Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it.
So yeah, as you can imagine, this is not going to scale up very well. 30 frames a second and hundreds of bounding boxes per frame, it would be a nightmare job and you just can't get very far with it, even with 1,000 people working on it to do the labeling. So what do we do about this? Well, we move to 4D labeling. That would be vector space, right, 3D video sequences in time, which is the fourth dimension, rather than 2D images.
So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject.
Once something is converted into vector space, you get a top-down view of the scene that you can label fairly easily, and it'll track the labels through the sequence after initial labels are given. And in case you're not thinking about all of this, this is based on the foundational ability Tesla has to change 2D images into 4D vector space sequences. And you can see the video on that if you're interested. This step is the key takeaway from this section of the video, as with most of the Tesla AI Day thing, is that labeling, just like driving, is being done in vector space, not image space. So again, you can think of converting all of these images into a video game-like level where object position is known as a matrix of numbers, not an image space where it is a group of pixels that changes with every frame. This vector space labeling is then reprojected back into image space for scene recognition, but it is automated in that it auto-labels all of the image frames once the vector space labels have been keyed in. Again, none of the labeling that Tesla currently does would be possible without the vector space transformation that happens first. And really, who else has anything like this available to them? Anyone? Anyone? Bueller?
Bueller? Bueller? Bueller?
But wait, there's more. Humans are still pretty terrible at working fast. We can understand things easily, what Andrej terms semantics, or this is a curb, this is a traffic cone, this is another car, etc. But we suck at repetitive tasks, and especially going fast. So why not get humans and computers working together?
But even this, we realized, was actually not going to cut it. So, because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space datasets.
The obvious solution is to have some form of auto-labeling that humans can preside over to ensure quality data. And at this point, Ashok Eluswamy, Tesla's director of Autopilot software, took over and explained how they're accomplishing this.
So even though we have lots of human laborers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto-labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45 seconds to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks.
So first, as I noted before, he said that they're using 40 to 60 second clips. This is massive. It's a massive amount of data to take at a chunk, so just wow on that front alone. And also note from this picture that they're not just using video, but GPS and IMU and other data as well. In other words, this is extremely rich information that they're providing to the labeling system and then to the training. And just as a quick reminder, the IMU, or inertial measurement unit, can tell how the car is oriented, how it's accelerating, etc. And of course, the GPS can give you a general sense of where the car is in the world. And this general sense of where the car is actually really helpful when multiple passes by different cars are used to enhance the quality of the data. And you can look at my vector space video for more on this, or just wait till later in this video because I'm going to talk about that again in a moment. Ashok also says that they get this data from the fleet as well as targeted engineering cars. Again, that mention of the fleet is a huge thing that just kind of flies on by, and this is where Tesla's data lead comes from, obviously. I think it's worth noting here that this is all offline stuff. Some people are confused and think cars are training themselves and labeling data themselves. That is not the case at all. The data is being sent back to the massive computing facilities at Tesla's research headquarters. So the training and the labeling definitely not being done on your car, although your car can flag good data to look at closely. For example, places where a human intervenes with full self-driving, or where Tesla's shadow mode, full self-driving mode, diverges from the actual human driving. Anyway, these images and other data are used to create segmentation and depth maps, or pseudo-radar. The world around the car is transformed into vector space, as you can see in the right-hand images, and it's segmented into objects that can then be labeled automatically by the computer. That means that the computer must recognize what all these objects are, of course, which is pretty darn amazing. Note in the bottom right of this image that it's mostly accounting for moving objects and kinematics in labeling, while the top right image focuses on the static world and the ego car trajectory. In other words, roads, curbs, parked cars, etc. that don't change. Of course, as you might guess, to make all of this happen automatically is incredibly complex, but it's oh so rewarding when it works. You can scale things up, guaranteed if it works, which means that you can label many more videos than a human ever could. Ashok then gets into the weeds about how this is being done, starting with road reconstruction. I'm going to skip this part of the video and just touch on a few of the highlights, but I highly recommend watching that part if you're really interested in this stuff. But I highly recommend watching the AI Day video linked in the description if you really want to get into all the gory details. Anyway, at a high level, the road is represented as an implicit surface using neural radiance, which is a technique that was just invented like a year ago. So talk about cutting edge. But anyway, this allows one to project points onto an implicitly defined surface, which is the top right in this picture, which provides an implicit Z, or third dimension. And then you compare that to a neural network's prediction of the surface and the class or type of elements of the surface, which is shown in the bottom right of this picture. In other words, the neural network will predict things like road height at a point, curbs, type of surface like asphalt, cement, dirt, etc. And then you use a loss function to train the neural network to get better at predicting all of the elements in the scene. This is a bootstrapping type procedure to functionally label a road surface and all the static objects around it, which is pretty amazing. And the results speak for themselves. The example Ashok shows is impressively exact in determining the road, the line markings, and the curbs.
Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So a single car driving through some location can sweep out some patch around the trajectory using this technique.
So as you saw, this is really impressive, and it allows a road to be reconstructed from a single driver driving through once, as opposed to the likes of Waymo that have to have exact LiDAR mappings of any area they're driving in and hope nothing changes in between times. But hey, while we're at it, why not combine the data from many cars that go through the same place?
But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HT maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer.
So you can see here how Tesla uses multiple cars, or maybe the same car at different times, to see different aspects of the same scene. In other words, you could imagine like driving in your neighborhood over and over and over again. So the labeling system can learn the labels of the scene better and better because it sees more and more of that scene with each car that passes by. So this obviously makes the labeling better, but there's another huge advantage that Tesla really doesn't mention. What became clear to me watching this over and over again was that this reduces the amount of data Tesla has to label and maintain. In other words, the data from many passes can be combined into one master pass through the scene, and this is labeled once or refined over time. So that means you don't have to label 2+ billion miles of driving, just the, say, 500,000 miles of road surfaces in a given country. In the end, this is much less than having to label every bit of data from every mile driven, and it makes the problem tractable. In other words, there are a finite number of kilometers or miles of road in the world, and eventually all of them will be driven over by Teslas. And then you use the GPS data to know when another car drives over it, and you refine the data there and you label it better, and again, and again, and again, and eventually you get immaculate labels for almost everywhere on the planet. Of course, things change over time also, right? But the basics are going to be there. And this gives you the ability to focus on labeling edge cases in time as well as in space, which is much more targeted. Now, I want to make a point here that this is not a high-definition map that the car is driving on, like Waymo. This is a way to get very high-quality data labels and to reduce the amount of labeled data to one master data set per given area of driving, which again is a massive computation and data savings. So the takeaway here for those who complain that Tesla just has too much data and there's no way that they can utilize it effectively is that they are utilizing it effectively. They're combining all of these passes of driving into master sets of labels and things like that so that they can much more efficiently train. And then of course the next really important part of this is the auto labeling. Then, as Ashok says, humans can now look over these auto labeled scenes and they can clean up any issues with them. This is a much more efficient use of humans. And also it's actually somewhat common in research these days. It's called human in the loop training. And essentially computers do most of the work, but where there are problem areas or where something is flagged, then humans intervene at these points and only at these points so that they're using their time the most efficiently. But what about things that aren't the road surface?
We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world.
For anyone who's worked with point clouds, this is a pretty insane density of points, right? Each point is being projected out from the ego car into 3D space from 2D car images. Again, they're being transformed. And points are even being placed in featureless places like the road surface. This is really hard stuff to do. And then what about the humans and cars that actually move? And what about occluded objects?
One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics like velocity, acceleration, etc. One more advantage is that we can have like different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they're occluded. So this is a massive advantage.
I love that Ashok says we get to hack time with these videos. In other words, since these aren't being used in real time, in other words, they're being sent back and they're being worked on, offline essentially, the network gets to look ahead to see where things will be in time, and it can use that to sort of back train itself in time. Andrej Karpathy has talked about this subject before, and if you want to look at some videos that I've done on that, you can check it out up here. But back to AI Day, you can take a look in this picture and you can see that people across the street in the crosswalk are still there as the woman and then the car pass in front of them, and how there is a vector space representation of the entire scene at the right. This is what the ego car, or the Tesla that's in red, knows about the moving objects in the scene. And also note that each moving object has a trajectory line, a thing that's sticking out in front of it, that annotates its velocity in addition to its position. And that these can actually be curves as well as straight lines, which is super cool. So this means that labels can include velocity data, which helps the system to train on kinematics as well as stationary aspects. And that's pretty darn important. So now if we put the moving objects and the static scene together, we get incredibly dense, accurate data sets to train on.
Combining everything together we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips and then train our video, multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car.
So note in the big top-down vector space version in the middle of this picture, the road is identified, each car is identified, pedestrians are identified, and even a cyclist is identified, along with some basic building and light pole objects and such. And that velocities are identified for each object as well. In other words, without human intervention, this scene is now properly labeled for training, including object identification and also object velocity where appropriate. And of course, since this is on a computer, it can be done over and over again very, very rapidly. This is true 4D vector space auto labeling. It's consistent in time and space, and the neural networks can train on them extremely efficiently. And frankly, the results are pretty astounding. And they explain how radar is not as necessary as others have thought.
We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably, because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions.
So in that sequence, we have a situation that seems to need radar of necessity, but it's not. And the fleet can make that happen in a very, very short time.
So what we did, we asked the fleet to produce lots of similar clips. And the fleet responded, it did. So it produces it produces lots of video clips where shit's falling out of all other vehicles. And we sent this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this.
All you need with this system is a few lines of code shown at the left, and you can request as many of these clips as you want from the about 2 million Teslas on the road right now. So what you get is you get 10,000 clips labeled in 1 week of snow falling off the back of things, just by asking. But not just snow off of a truck. They asked for 200 other obscuring edge cases and did those too. This would have taken years to find and more years to label by hand with a smaller fleet, and Tesla did it all in just a couple of months. And they got rid of radar just like that. And really, who else out there can do this? And then Ashok transitioned to speaking about Tesla's use of simulation to add to their incredible data collection and labeling techniques. But we already covered that in this video up here. And just as a reminder to some people, Gordon, the simulation is in addition to real-world labeling, just so you know. So anyway, data labeling isn't what the cool geek kids are doing. It's not building a robot or making an insane HydroNet neural network, but none of the other stuff works without data. Machine learning today is training novel architectures on big data, and Tesla needs the biggest data to solve the biggest problem, that of real-world autonomous driving. So it actually seems appropriate to me to close out our journey into AI Day by talking about data and labeling. It's something Tesla has in spades, and nobody else has anything close. And no one else can do this trick of turning 2D images into labeled 4D vector space data. So who else is going to solve real-world full self-driving besides Tesla? I don't think anybody can. And just as a final note, thank you Tesla for sharing such detailed and amazing information with us lumpen proletariat. We really do appreciate your candor, and I for one can't wait for AI Day Part 2 sometime. All right, I hope you found this episode and quite frankly this entire journey through AI Day fun and enjoyable and informative and somewhat inspiring. If you did, please do like the video so other people can find it, and definitely consider subscribing for more of this. As always, a huge shout out to my patrons on Patreon. Thank you all so much. You all are wonderful. There's been a lot of new people that have come on board recently, so I want to do a new Patreon patron shout out with the end of AI Day. I think that's appropriate. So anyway, those patrons are Luke, Brad Moore, Roger, Stephen K. Stevenson, Benjamin H. Berry Jr., Phil Krug, Mike Sherman, J.I.O., Hydra Fighter, and Rick Olson. Thank you all so much for joining. And of course, if you want to join the club, just check out the link in the description. And if you're interested in some awesome merch, check out the link in the description. We've got the TeslaBot t-shirt, which is super popular these days. Don't mess with Tesla. Lots of other t-shirts, tumblers, mugs, etc. So check out the link in the description and help the channel out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200. And fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you check out the link in the description, you can see how going shopping for a Tesla, a solar roof, a battery wall, or anything from Amazon helps out the channel. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.